Jewel spheres. Take it
Nice.
away, Shane.
Thank you, Kat. That was excellent. Bring on over to our live stream view. All right. So, thanks everyone for coming, tuning in. This is going to be a fun one, I think. It's mostly going to be a amalgamation or accumulation of the last few Prezis, right? We started with a good old great switcheroo when we talked about how the globe was really just a celestial sphere mixed and match back into maps and cosmography and how we greatly relies on the celestial sphere and angles to the stars. And then most recently our terrestrial sphere, the geodetic datum. So now, with all those prezis, we have the components to put together the model that would create the globe, right? Because without these two things, there is no globe. And separately, they kind of are used independently, but when used together, do you get to create the globe. So it's the combination of the terrestrial and celestial spheres. Real quick, if we just do a recap on our terrestrial sphere, we knew that it was a geodetic datum that was WGS84, and it was tied to damn near everything in the world. Like if you used a map, if you used a GPS, if you were navigating, if you had anything to do with cartography, anything to do with aviation, maritime navigation, surveying, geospatial analysis, robotics, anything in the world that was done on maps was using our terrestrial sphere, our WGS84, which is a reference ellipsoid, which is how they use the graticule, the longitude and latitude system. So we brushed up on that. We remember this is how we concluded. It was a ultimately self-referential framework, which is internally consistent, meaning that it doesn't actually track the surface of the Earth as curving. Our terrestrial sphere model, made up of longitude and latitude, is a reference ellipsoid contrived by assuming a model, essentially. Now, we also touched on how they confirm that model. Like once they assume the Earth is a terrestrial sphere, how did they make sure that they were correct, mind you? Well, they measured meridian arcs, right? Meaning that they took a very small position and they measured a very small portion, and then they calculated the distance between those 2 points using latitude and astronomical observations. So they would use the angle of the sun or the stars above the horizon, and they would measure a very small portion of, say, a terrestrial meridian, or from the North Pole to the equator. And they measured just a few kilometers, 1 or 2, which is about 1% of what they were claiming to have measured, right? And they're going to calculate all the rest. So they measure 1%, calculate all the rest based on astronomical latitude determinations. And then, of course, the vast majority of this arc length is inferred from calculations based on our celestial coordinate system. Now, we knew that this is what is at the heart of the modern ellipsoid model, or the WGS84, is because the Clark ellipsoid actually became the North American datum, NAD27, which then became NAD83, which then, of course, after evolution, turned into WGS84 way down the line. So here's how it was initially contrived. Here's how they confirm it with the calculation with a nice R value. And then they use, based on their ellipsoid model, they use this tiny measurement of the 1%. They feed it into the equation, and then they get the rest. And that's how they confirm the terrestrial sphere. So that's a quick recap. Bring us into the star of today. We got our boy Ptolemy, who put forth a book in antiquity called Geography, also known as Cosmography, actually, or Geographia and Cosmographia. So our boy Claudius Ptolemy was said to have, lived back in ancient Rome and is the father of Western cartography because he is the most famous for this book called Geography or Cosmography. It's interesting that the two are used interchangeably, right? I always say that it's more cosmography than cartography, but his book actually could have been called Cosmography. So it's well known because it's the oldest known treatise on geography and cartography that's ever been compiled, and it has quote innovations in map making. And we'll give you a little hint: the whole innovation was that it introduced Latin long and the graticule way before this time, and then of course influence on all cartography and geography today, and of course the term cosmography. So if you were to read this book, of course it's the only one to have survived from the period, and it's one of the most influential scientific works of the time. Of course, it was supposedly written in 2nd century, and it was, it has chock full of, I think, 8,000 longitude and latitude measurements. So he's got the whole known world marked to the graticule 3,000 years before longitude and latitude was actually unified, right? So that's interesting, useful. What a guy. He championed the use of astronomical observation and mathematics in determining geographical locations. So, said in other words, he's the father of cosmography, right? The father of combining the celestial and the terrestrial in terms of cartographical and geographical locations. So he's mapping the known world based on the sky. That's what he's famous for. And that's what the first maps did. And that's what he's this claim to fame is. He put forth the blueprint for all modern cartography. And in there is the two-sphere model, right? If you read his book, he actually says, hey, you can't go any further. You're not going to understand anything unless you accept and understand the two-sphere model of the cosmos. So in Geographia, he lays it out, the terrestrial and celestial spheres. Before he lays out latitude and longitude or anything, the framework with which you need to understand everything he's putting forth is the two-sphere model of the cosmos. That's what he calls it. The two-sphere model, the terrestrial and celestial sphere. So you look into a little bit, of course, he goes into the sum of latitude and longitude. He does it in stadia. He marks the locations all over the Earth. We'll go into that in a little while. Everything that he does, though, is based on astronomical observations. This book isn't actually even really his, he says. It's put forth based on someone else, and he takes credit for that. He says that in his book. Not a big deal. Of course, he has 8,000 places through combination of astronomical observation, meaning latitude and longitude observations for all of the known places, landmarks, cities, travel spots, etc. So in doing so, fathered the graticule, right? Introduced the grid system that used commonly off, say a prime meridian or whatever you want to call zero, to organize these measurements. And he would reference in other places to location to the heavens, right? So he's the first to use the terms latitude and longitude in mapping, which we'll definitely get to later. But of course, using the heavens to map the Earth, like that is what the graticule is doing. That is what the two-sphere model is doing. So what the ruck, if we go through, is it a real book? Was he a real guy? Are the observations consistent? No, it's a host of, say, interpersonal observations where it could be a collection of other writings. The whole book is just sort of a conglomeration of globe lore. But we'll say that one guy wrote it for the sake of history, and we won't say that Myrnus of Tyr did anything, even though that's with whom he stole all the work, because from its details as the places in the arrangement were taken from an earlier cartographer, Myrnus of Tyr, right? So, and then of course you have Hipparchus, who used all of the observations as well. So all of the ancient Greeks relied on each other for their veracity and for all their work. So let's just say that they're all real for now, even though evidence points to not, right? It's got a parenthetic style of writing, meaning that it could be a person with a split personality or many different personalities in one, or it could be just a recollection of many different people under one. But not super important for our examination today. This is, of course, he put forth the graticule. This is Ptolemy's second projection. He put forth a couple of projections. You see this one on Wikipedia. This is the one on the cover, credited to him all the time. You'll notice it's not the full world. It's the tiny world that he knew, measured, and projected with his grid graticule. Now, the other thing that Ptolemy is famous for that is sort of related, but is not, and if you mention the two-sphere system, someone might bring up this. And this is sort of his geocentric cosmology and how he would explain the motion of planets, and it would deal with exocycles, epicycles, and retrograde motion. So that's not what we're going to be talking about. That is something that he put out, and if you do refer to the two-sphere model, some of the results you might get might refer you to this. And again, related, but not what we're going to be talking about going forward. We're going to be talking about the two-sphere model of the cosmos, the celestial and terrestrial spheres. Although he did put forth a nice geocentric model for how he thought the world worked and how the planets orbited. One other thing that Ptolemy put forth was another work called the Planispherium, or the flattening of the sphere. Literally, the father for the planisphere, right? The stereographic projection of the celestial sphere onto a plane. It's exactly what this is. And he wrote the book, which was, the basis and the infrastructure for the planisphere. He wrote it in a book called the Planispherium, which, again, the flattening of the sphere. I thought that was neat. It's another thing that he's known for. It really embodies our sort of conceptual of the cosmos. So you have either an assumed curvature to the ground that no one ever sees and assumed parallel light rays to make everything work, or you have a local light source and you have varying distances with latitude for stars. Right? Those are the two conceptual models you get from flattening the sphere. So, again, we're talking about the celestial and terrestrial spheres. Of the celestial sphere, quick recap here, is again based on the coordinates of the map. It's the observations of the sky. You got red ascension, declination, stars, where they're going to be, what time they're going to be there. And that's based on regular flat Earth hemispherical observations of the celestial, right? You have your zenith, you have the celestial equator based on the terrestrial equator, the apparent position of a star based on declination above the horizon, and all of the actual observations based on this over here. And that's how you get this, right? They just use multiple observations of alt-as, and they contrive anything below your plane has a negative z-axis, and they will put forth this conceptual model. Now, the terrestrial and celestial spheres are not real in any model, in mainstream, in books, in historicity at all. They're both conceptual models. So this is our conceptual celestial sphere, and this is our conceptual terrestrial sphere. Again, most known as the graticule. It's the terrestrial coordinate system. That's most directly how you define it, latitude and longitude. Also known as the graticule, right, which we always call our WGS84 graticule. Here we go. So the terrestrial and celestial sphere. These are the two things that we're putting together. These are the two things that Ptolemy put together to create the first and the first book put forth ever on cartography called Geographia. So within his book, he used the graticule, or latitude and longitude, right? He imposed a grid parallel of latitude and meridians to form a curved grid, which he then projected his map projections on. So he made his coordinate system, and from that, he projected his famous two map projections, supposedly. So if we were to look at what they were doing, in the northern hemisphere, right, they would use the North Star to navigate, or they'd use the sun to get their longitude. They can use the time of day, right? They get the length of the day, the longest day, and then they would use other celestial bodies, their positions, use the gnomon or an astrolabe, which is just a updated planisphere. And from the 15th century, they were navigating the sea without any sort of unified latitude longitude using just the basic methods. But when Ptolemy was putting forth, they apparently were navigating using his spherical coordinate system. Everyone locally was using his personal longitude and latitude. I just find it more likely that everyone was navigating based on their known methods at the time, and that the whole story of latitude longitude being created 1700 years before it's used is a little arbitrary, but let's just assume that that's right. If we go to a modern understanding, the latitude and longitude system is spherical. It's a coordinate system. It is spherical without a doubt. It has great circles. It's used with spherical trig. The WGS84 uses things like Haversine, right, to get the distance between 2 points on a conceptual sphere. So all of those are indicators that the latitude longitude system is definitely curved. But was it curved back in this time, back when they were using, sticks and gnomons and celestial observations? Probably not. I don't think anyone was using a spherical coordinate system and then translating coordinates from two sphericals to get where they were. I think they were most commonly using the old school definition, right? Latitude meaning breadth or width, right? Just how wide something is. And longitude meaning length, or long duration, how long something is. That's the most basic definition. Even if you were to make your own grid, you would just be worried about how wide and how long. Now, as we were going over in our debate, the latitude and longitude system no longer means that. Latitude and longitude are very specifically defined in modernity as the angular separation from zero, east to west, and north to south, respectively, right? Latitude is east to west, longitude is north to south. Now, these are definitely definitions tied to sphericity. Right? This definition makes no sense unless used within this model, especially that, look, they're already saying we know how long each degree of latitude covers on the Earth's surface. They're invoking the meter and a proportionate ratio of the terrestrial meridian to say we know exactly how long this is. We know that the only metric unit tied to a physical distance on the Earth is the nautical mile, which is when 1 minute of arc, which, they would have to say travels 1 minute of arc along this much of the sphere, and they know that it equals this, right? So the question is, when did they switch from what used to be called just breadth and width to length, right? Where did they switch? Well, if you look into it, it started to be used right about after the Renaissance, which ties it to about the 16th and the 17th century. That's when it started to deviate from the old school meaning into the modern definition of angular separation from the equator, east and west, from north and south, and was probably, it says, emboldened by the work of the Renaissance cartographers and astronomers who would describe the mathematical grid system for mapping the globe. So anyone using the graticule, anyone from the Royal Society or from Newton's time, would be pressing this model. And that's when the definition changed. And of course, all of academia being slowly controlled by the Royal Society would make that an easy change to happen. And then by the time of the Meridian Conference in 1884, they made it official, and they made absolutely sure that these definitions are now forever tied to sphericity. And that memory holds history, right? But we're talking about latitude and longitude as the grid because we're remembering that it equals each other, right? The latitude and longitude system was reverse engineered from observations of the sky, particularly Polaris, and is not actually based on physically measuring Earth's surface or Earth's shape, right? It's spherical Earth is imposed on flat plane measurements and only through correction angles applied over long distances, which we see in geodetic surveying extensively. They take planar measurements and they apply through mathematical corrections and astronomical observations calculations that would then impose the sphere onto those planar Earth measurements. So then the premise of a presentation becomes the curvature of Earth is an illusion created by astronomic and geodetic measurements artificially aligned to make the graticule conform to celestial models. That's essentially the premise of what I'm putting forth here. And if you look at how, say, celestial navigation works, right, it works because they have converted the geographic to the celestial. They say for every point on the Earth, specified by, say, phi and alpha, there's a unique point in the sky, and that every point in the sky uniquely corresponds to a point on Earth's surface depending on the time. Because of that relationship, and again, this is the one-for-one relationship, which is at the heart of celestial navigation. This is in fact how a zenith position is defined, right? A star has a unique position on the Earth. That's how the models are linked. That's how latitude, longitude equals the celestial observations. Now, we go back to how Ptolemy was using it, right? We remember he's using the angular distance in the definition of modernity already, but he's using it in the same sort of time scale. He's using 15 degrees for 1 hour, even though he defined a different prime meridian. He's using the same equivalence of longitude to time, even though he says it could not measure longitude directly. Instead, they estimated it from things like lunar eclipses, Jupiter's moons, lunar transit methods. That's what they say. So they were using latitude and longitude based, essentially they were using latitude, elevation angle of a known star, and then a time component for when it would be there, which is in fact exactly what we do today, right? Remember the story is that the graticule wasn't created until about 1714, when they had the board of longitude try to get the distance of longitude between a degree of longitude at sea down to half a degree, and they issued 2 million gold in modern times to try to get the accurate timekeeping. And because it was such a problem, they had to find this out, right? That's what they were putting forth. So we have this juxtaposition of in prehistoric times, not prehistoric, in Roman times, 100 BC, we have Ptolemy with his graticule defining latitude and longitude on a sphere in 90 degrees and cataloging 8,000 locations relative to the heavens on Earth. And then for, say, 2,000 years, nobody does anything. Everyone navigates. Everything's fine. But then we need, longitude comes again. We need this universal defined longitude system in 1714. Now, the reason why they say they needed that is because there was accidents, right? There was treachery. There was misgivings. People were getting lost. People were sailing into rocks. Ships were, apparently. Now, again, everyone in Ptolemy's time was fine because they were using his graticule, right? And then somewhere between 100 BC and 1714, everything went to shit, and nobody could find their way at sea all of a sudden. This is the historical narrative. So then, even with, say, Lewis and Clark, they couldn't read, they couldn't know where they were, right? Because they had to get accurate within a fraction of a degree, and they were using tools that were notoriously wrong. And so they had this article, and if you look through the historical record, they say it was trouble. There was a whole bunch of trouble. But if you look at who put forth the warnings of the trouble, it was entirely the Royal Society here, right? So before the establishment of the Board of Longitude, there was widespread recognition of the inability to accurately determine longitude. This is the story. And then they said that, including figures, published dire warnings about the dangers of poor navigation, and then would publicize wrecks, would specifically talk about and issue press releases and pamphlets and talk about all these tragedies at sea. So either there really were a marked increase in tragedies right before 1714, which necessitated the unification of longitude so that everyone could navigate, or a normal amount of crashes happened, and our boys at the Royal Society propagandized some fear porn about some crashes at sea so they could put forth their pre-planned solution. Now, that's a conspiracy theorist theory for you, but if we look around today, we usually get manufactured problems and prepared solutions. And this seems to be exactly that. Look, if there was a normal amount of crashes, all they would have to do was to focus and publicize these crashes to drive the amount of fear that people would need to be able to fix the so-called longitude problem. Now, any questions so far?
And also an incentivized reward and a fine if you didn't use their system afterwards.
Yep. Afterwards, you were monetarily punished for not adhering to this because you were putting your shipment at risk, Peter. If you didn't conform to this, you could be this ship right here, right? Your shipment could hit the rocks and my money could go to shit.
Right.
However, if we were to look into it a little further, through antiquity, up through the 1700s, people were navigating things using windrose lines, or what's called a rum line network. This is super interesting because if you look at old maps, you'll notice that you'll see things like this, right? You'll see this compass rose, all these sort of meridian lines drawing out in incoherent distance, and then some land with some marks. If you were to look into it a little bit, they would use these to plot courses and maintain bearings, and they'd use with something called the compass rose, which had enough angles that they would line it up when they got to one of these junctions, and they would line it up right over their position, and then they would get their new heading from that. And then doing so, they could dead reckon, use latitude and longitude, use basic thrust observations and the known maps, and never need a spherical coordinate system, the globe, or unified longitude to get anywhere.
That is really interesting. I'm going to look into that.
Right, so they have this thing called the rum line network, and they were supposed to be used. They would maintain courses that would be a constant compass direction for mariners. So essentially, it would be used just like this. You'd have this on the ship. You'd take your map when you get to your position based on where the latitude says. You'd line this on your map. You'd plop it down over a spot, you'd get your bearing, you'd say, okay, I got to go this way to get my next position, and from there, you get to the next position. Now, there were many of these on the map, so you'd only have to go from one to the other, and you could dead reckon that amount of time either way. So they're actually called... Go ahead.
Are the center points of those rum lines or compass roses, are they GPs of stars, or no?
That's a good question. I don't know. They could be. They were obviously well-known positions that everyone could get to, so that would make sense. I didn't actually look into it because all they have is like artistic components today. If you look at what they have on Wikipedia, these are more like they got pictures, they got tents. This is it's not really a to-scale map. They were trying to show it to look like this on purpose, but there are to-scale local maps where you can use rum line and compass rose to navigate. But yeah, where the point is chosen to put, I'm not sure what the terms are.
Yeah, I want to figure that out. Sorry, I never heard of these. These are interesting.
Yeah, they're called Portorian charts essentially, and they call them early nautical maps, but they were literally just networks of rum lines or rum plum rose networks. So if we look into that, then we have to question what was really happening at the time of the longitude for this to like. So was everyone really running into rocks everywhere they went all of a sudden up until 1700, or was there a couple crashes that got publicized hardcore by the dudes who wanted to push an agenda that had a goal? So there was, ships often ran ashore because navigators could not determine their east-west position. And then they have, if you look into it, there's one example. There's only one. It's 7 years before the Border of Longitude, right? So they're known for the thing. And 2,000 people died. And it was the silly naval disaster of 1707 with 4 ships died. So it was miscalculated based on bad weather. So, I mean, even if there was a bad storm and 4 ships lost, they milked the hell out of that episode and told everyone that it was because longitude wasn't accurate enough. And then they put forth this solution, the Board of Longitude, which started the whole thing. That's my take on the historical record. And there's a couple other incidents, but I mean, if you compare it to how many incidents there were before and how many incidents there were after, a completely normal amount of crashes happened. But in this whole decade, there's nothing out of the ordinary. So it's data manipulation at its finest. Sometimes people crash, sometimes storms come, and sometimes people do. Sometimes cargo is lost. That doesn't mean that it was directly a cause of the longitude system that they had yet to implement.
Dude, I totally thought you were
that
being. I thought he was being cheeky when he said this a silly naval disaster of 1707, but it's really a silly naval disaster.
Silly. I don't know.
That's hilarious. All right, go ahead, Shalom.
That's the most famous one.
Oh no, I was just saying that makes total sense to me. Use crashes that happened and that would normally happen over the course of time, including crashes that probably didn't happen, as a form of propaganda leading up to this standardization.
Yeah, I wouldn't put it past them to cause a crash, right? To like have a captain run a ship ashore or whatever, and then use that, or just find a crash that happened and milk the hell out of that. Either one, I think, is totally possible.
Even more hard to validate one way or the other if you're just a normal everyday village person.
Yep. So they scared up everyone into the world. They were like, "Listen, all these crashes are happening everywhere, all over the world, guys. We need longitude. Everyone, come fix our Board of Longitude problem. Don't worry. We're going to invent a board. We're going to invest the power in ourselves. We're going to elect ourselves governor, and then we're going to make some laws for the world to follow right after." So that's how that went down. And again, this is all based on this amalgamation of these two conceptual spheres, right? The celestial, which is right ascension declination, and the terrestrial, which is just latitude and longitude. The way that these two relate is through the equator, right? They're both reflections and unified off the terrestrial and celestial equators, respectively. The celestial equator is just a mirror of the terrestrial equator. Remember, these two models are concentric, one's above the other, and the celestial just mirrors the terrestrial. So we have the equator on the terrestrial sphere, which is, of course, marked by sun angles in the coordinate system. And then from that, you project the celestial equator. And these equators are the unifying guidelines for measurements between different hemispheres. So if you didn't have an equator to mark your right ascension from, then you wouldn't be able to tell a friend in a different location where he was. You wouldn't be able to relate that to him. So, but again, the comparison here is each uses a fundamental circle. Hold on one second. Yeah, each uses a fundamental circle. Is essentially like a great circle, but has centered in zeros for Greenwich meridians for longitude. Time is intrinsically linked to both of them through sidereal rotation. All of celestial navigation involves measuring the angles between these bodies and the horizon, and then comparing these observations with tables based on the right ascension and declination, and then you translate to terrestrial latitude and longitude. That's essentially the modern method of celestial navigation, right? You take local alt-as observations of a star, you mark it, and then you convert that to latitude and longitude based on the time and the local hour angle transformation and the Greenwich meridian time. That's why it's so important. So latitude to declination is like a 1-for-1 transfer. Longitude to right ascension is the other transfer. So that's equating these two spheres, right? We have the terrestrial and celestial sphere, and here's the math that links them together, because this is right ascension declination, and this is latitude longitude, and this is latitude to declination, longitude to right ascension. So they're identical 1-for-1s. Now, our basic model is that coordinate systems based on angles to the stars assume curvature, right? You're inherently assuming and dealing with curvature of the celestial sphere. Whether that is that actual curvature of the Earth? No, it's an optical curvature effect from the effect of a rising and setting celestial body, like the sun. Now, the premise is that this is the only thing in the world through each coordinate system that is curved. Nothing in reality is a sphere. Right? We have a flat plane. We make elevation angles to stars. We have everything is observed flat. We have regular planar surveying that always adhere to a flat baseline up to, say, 100 miles. And then past that, you have flat baseline measurements adhered to spherical coordinate systems. So nothing in the world that we deal with is actually curved except for this optical effect of rising and setting, right? Let's go here. So because each system defines a fundamental plane, it's just based on flat Earth observations. Now, you are using spherical trig to account for the curvature. And again, the only thing that is curved are these coordinate systems. So back to our old model then, if we're using rhumb lines and compass roses and we're taking elevation angles to stars, then can you actually get your location today based on a single observation? Because the modern method is no, you'd use 2 or 3 elevation angles, right? You draw concentric circles, you get circles of equal altitude around an observation, and then intersecting those circles, you'd be able to gauge where you are on the graticule. But if you already knew, say, your latitude based on an elevation angle of a particular star, like Polaris, and if you happen to know your time based on, to a degree of precision that you wouldn't, then sure, you can actually do such navigation based on a single observation by assuming that latitude is the elevation angles. Of course, the preface would be don't do that. This is only true for Polaris and near the North Pole, which we know, which is fine.
Galley to the rescue.
Oh, you're back, Shane.
Let's go.
What do you know? I was gone?
I was streaming your YouTube.
Yeah, your Discord crashed.
Oh, for how long ago?
About 3 minutes.
Okay.
Yeah.
Did you guys see this one then? Yeah? No? All the way back here?
You're not sharing.
Oh.
You're not screen sharing anything. You gotta close it and reopen it probably.
Well,
really crashed.
the good thing is the stream is fine.
It was solid.
Yep. All right. Cool. Wow. All right. Just stop this. Share again. You guys see this slide?
Yeah.
And did you see this slide?
Yep.
All right. Then we're good.
Hmm.
So the question is, if you're using old school run lines and compass rose and an old map and Boolean charts, then can you just make an observation of a star and calculate where you are? You can even do this today. You're supposed to use 2 to 3 observations of a star, compute circles of equal altitude based on where those intersect on the graticule. You can plot your position. But if you were to make an assumption of, say, in the northern hemisphere, if your star equals your elevation angle like Polaris, then you have a component that you wouldn't need the 2 intersections for. You can actually do some calculations to figure out where you are based on a single observation. So if we can do that today, then the question is, through 100 BC through 1712, with people who have wonderful charts with a compass rose and a rumline network, making stellar observations to their star with a nice chronometer or even any sort of timepiece, then why would anyone need the globe? Why would anyone need a unified longitude system to have these crashes not happen if everyone's mapping the world with local shorelines, right? I would argue that that's completely fabricated as a need, and that this whole thing was a problem, reaction, solution sort of iteration. So then, of course, we have celestial and terrestrial sphere being 1-for-1 to each other. That is the premise of the presentation. Of course, premise of the modern global model. We know that it's a 1-for-1 correlation with the celestial sphere because the datum that we have here, the WGS84, is literally latitude and longitude defined as the Earth, and then we have it mapped to the sky. So, of course, as we said in the beginning, neither one of these are real. These are conceptual spheres. We have the story of 2 conceptual spheres here, the terrestrial and celestial sphere, when put together, would make the globe model. Now, we know that both celestial spheres based on observations like this, the hemisphere view, anywhere you see, and then your local horizon, elevation angles off that. From these observations, they create spherical coordinate systems with unifying factors like the celestial equator. In this case, you can use a galactic equator. Without a unifier, like a unifying equator, then there's no way to relate, say, observations of way south to observations to a friend way north. Your local alt-as coordinates wouldn't mean anything unless you can convert them based on a central unifier. So from that, we have alt-as, or altitude, azimuth, and horizon, which is the basic coordinate system of flat Earth, I would say. And then you have right ascension declination, which is the celestial sphere, which is the 1-for-1 correlation of what you observe in your alt-as. So both of these are based on flat baselines, and both are spherical models that have math to sort of predict a z component that is negative when the celestial observation goes, quote, beneath your feet. This is based on the circumference of this circle, but if the star is just traveling on Earth on the same circumference, and as it rises and sets, as it comes and goes, then the circumference is the same, and that's why the prediction of a abstract spherical coordinate system makes total sense on flat Earth. So again, we have alt-as. This is the basic coordinate system of flat Earth. You make observations from this guy in the middle, and then from that, you create these 2 coordinate systems in their entirety. Now, what they're really based on, though, and what it is at its heart, and if we bring it back to cosmography, it's based on the stars. This is you can create the whole globe model from this picture right here. This is just the sky, right? It's the celestial spheres flattened out on a Mercator-like projection. Perhaps we're more comfortable with it represented like this, right? We have the outline of the continents. We can see that the stars at a certain spot, each one has its own latitude and then rotates around the Earth. From this, we created the whole backbone of the model. This is, of course, the same sort of image. We have the same star picture. You can see the Milky Way. You can see the celestial path. It's the path of the sun and the moon. Portrayed a little differently, say on a orthographic globe, it looks like this. Same data, you can see the globe almost forming. On actual orthographic, it would look like this. And again, just a regular star constellations map with our zodiac constellations over here in the middle. If we were to say get the globe from that and wrap it around a globe, it would look just like this, or like this, which is, of course, the globe model. This is the northern hemisphere and then the southern hemisphere, right? This is the concentric, I forget which projection this is, but it's typically the concave Earth model, where they have the two bipolar hemispheres over here. And of course, the same data portrayed on a sort of an AE projection. And this would be how the stars are. They appear at the same latitude and they always kind of rotate.
That's the one. And it's amazing because I'm looking back to going to my science classes. It's like it was in front of me the whole time. The teacher had on their platform, on their desk, they had two globes. Both of them had the lines on them. One was black with stars and the other one was blue with continents on it. Both the same size. And it was like right in front of me the whole time. Both of them spheres. Just one had stars with lines on it and one had continents with lines on it.
Yeah, I'm actually arguing that there was a period in 1700s when all the maps sort of looked like star maps, right? They all kind of came out like this. Where you look at a projection map like this and they'd be like, oh, look at this wonderful globular projection. And you're like, yeah, but it looks just like the star map. What do you mean? If I was going to do a double hemisphere star map, this is how I'd want to project it, right? I want to project it like this. So I thought it was kind of a goof that they would put, say, the land masses in where the stars would be. And then I realized, oh, well, it doesn't matter. They're interchangeable. Holy crap, it's the same thing. If you just keep looking at it, then if every star has a position on the ground and is inextricably linked, then if you're looking at it like this, right, if it's just spinning, then every star as it goes has a different right ascension. So if this star circles around, it's at the same latitude the whole time. It's based on 24 hours. So that's why you take 24 and you divide it by 360 and you get the actual sidereal 15 degrees per hour. That's how this works. It's at the same latitude and perpetuity for everyone, but at a different time. Right. And so again, this is the star map right here. Same thing. You got the zodiac and then you got the solar path. And again, if you look at it on, say, this is a globe sort of orthographic, a regular globe orthographic, the concentric sort of splayed out version, and then the A version, right? So it's played out that way. And there's a couple more star maps in here. This one is particularly good because you can see the zodiac. The thing you notice is that once you do this, the zodiac becomes visible for everyone. You can see that if it's this middle band of stars, then no matter where you are on the Earth, if you can see half of the Earth anywhere you are on the Earth, then this band in the middle is visible to everyone no matter where you are. And this one kind of really shows it, right? Here's the zodiac constellations as they are on the Mercator. Here would they be spread around the orthographic globe. And then here's the comparison where on the AE or on a flat Earth, these constellations would be visible to everyone everywhere. So we wonder why they had pyramids built based on Orion's belt. It's because everyone in the world can see it, right? Depending on this time of year, sometimes it dips north and south depending on the winter and the season. But for the most part, everyone can see most of these constellations everywhere on Earth. So that's why they're used for navigation. They're used for all sorts of things. They're used for really, that's a whole different presentation. Here's some more sort of star maps based on the projection. Here's what it looks like on the globe, right? This is what a typical star map would look like, just like this. That's a typical star map they do today. If we just a little tweaking, we can get it to look like this, which of course can give you this. So you can see how it's all related. It's all the same. They're all sort of projecting the same thing. I went through old school star maps. If you look at them today, they're presented like this, northern and southern hemisphere. And if we're remembering how the graticule can be presented and looking at it just like this, then we can see that it's actually the backbone. They're all the backbone of the same thing. This one specifically, you start to see all the patterns coming out, and you see the terrestrial and celestial sphere as the backbone for everything. Some of the older ones like this have pictures, right? The pictures represent the constellations, and they sort of have them on a zodiac wheel, but they're in their correct position in the northern and southern hemisphere. So no matter how you're looking at it, the celestial sphere mapping out has always given us the terrestrial sphere.
You may have seen it, but Amazon sells a globe within a globe. The outer globe is acrylic and clear, and it has all the stars on it. And the center globe is, the globe Earth with the continents and the oceans and what have you. But it's a globe within a globe, the celestial sphere and the spherical Earth.
Nice. That's exactly the right model, right? So they're not even hiding it. But it's kind of what Ptolemy's armillary sphere looks like, which is over here compared to a regular armillary sphere.
That's it.
Yep. So there's the model. You got the actual so-called conceptual Earth on the inside, the bigger conceptual no radius celestial sphere on the outside, and then the interplay therein. All right, and that's the modern version of it, sort of. And again, the two-sphere model that we're talking about integrates celestial and terrestrial coordinates to map the observable world, also known as cosmography. And again, we have the celestial sphere being contrived off hemispherical observations on a flat plane. And then you have your terrestrial sphere, the self-referential framework, internally consistent ellipsoidal model based on measuring meridian arcs and calculated from terrestrial latitude. And from those two together, you get the globe. Only to those two together, right? Only mixed together do you get the third conceptual sphere, the globe Earth. And that's pretty much all I got.
Awesome, Shane. Thank you.
Yeah.
Great presentation. That was awesome.
Nice. What we got for questions? Anyone?
I do.
Yeah, there's one person in chat. Their name is Gayfish Jaren. They said, you know, the Earth is mapped on a sphere, right? You can go anywhere in the world and ask anyone and check if it matches. You know it matches a sphere every single time.
That's a very good question from Gatefish Sharon. Yeah, no, I agree. The WGS84 as its self-referential terrestrial framework is very, very convincing, right? As we started off with the review, I think that I don't give it we don't give it enough credit, right? We accept the coordinate system with which we're presented, and the vast majority of our world presents to us in WGS84 spherical terrestrial coordinates. So even though it came from Gatefish Jaren, it wouldn't be a bad point, right? If you didn't look into it at any degree and you weren't even skeptical of anything, then you would accept all of this at face value. You would believe maps, cartography, GPS, navigation, Google Earth, satellites, anything that you do is actually giving you the correct position, and it's not just inferring a spherical ellipsoid model based on a datum, based on celestial observations. No one has the need to look into it that far, right? To go back to the father of cartography, to see what the two-sphere model was at its conception, to see what the world's oldest book on geography says about the two spheres, how astronomical is vital to the terrestrial, etc. Right? So I don't fault people who don't look into it any further and just think Earth's a sphere because maps work and my satellite tells me where I am. That's a fair point.
I got a question.
Well, I like
So how many fictitious observers does it take to make the celestial and terrestrial sphere work together? Was it just the one at the center?
Yep, you can use the same unified celestial observer. Fictitious observer, sorry.
So earlier you said the celestial sphere has an infinite radius, which right?
Yep.
So where do they only get the 3959 from 69 degrees per nautical mile?
3959, the radius, is actually never measured itself, right? They get that from the circumference, which they measure from sun angles. The Eratosthenes method is still like the best known method to quote measure the Earth's circumference. If you ask McToon, if you tell McToon no one's ever measured the Earth's radius, he'll be like, no, I have. And if you ask him how, it's because he took sun angles to the star to calculate to the sun rather, to calculate the circumference, right? And then from the circumference you get the radius plus 2 pi r, and then that's how you get the quote confirmation of 3959 is through sun angles and circumference.
Through sun angles.
Yep, only through sun angles. That's the world's best radius measurement system.
And to add to your question, Beast, so the celestial sphere is infinite radius, right? But then when you want to use it with the terrestrial sphere, you have to merge the two. So they do a geocentric coordinates transformation, which is where they're using that fictitious LAD in the center to set all their zenith measurements to stars at 3959 at that calculated radius based on the position of the sun. So
it's definitely all
based on the
related.
position of the sun. Wow.
Dude, that's
So how would you be able to tell the difference if it looks the same on ball or on planar?
very good question. My position is you wouldn't be able to tell the difference either way, which is how it's been such a convincing story.
So I was told because the
There
Earth
is
is
one-
mapped. If the Earth is mapped on a sphere, that means we live on a sphere. So are there any observations that do give you any type of exclusive evidence one way or the other?
Right. Well, as soon as you look for like surface of Earth curving, you end up a flat earther because there's none of it. It's never happened, and that's the big contention with all of the model is that actual Earth measurements never come up sphere, always come up flat. Only when you reference in relation to the sky can you even abstractly infer curvature, and that's how the whole thing sort of is built. But I do the celestial sphere having an infinite radius is a cop out, right? What that really is a mathematical equivalence of a flat plane with angles to the stars, because
Exactly.
infinite radius is just conceptually flat. So they trick you into thinking, oh, the sphere is so big it's infinite. Okay, well, what's a sphere that's infinitely curved? Oh, it's flat. It's a flat baseline. Okay, I got it. You guys got me right. Like, good trick, everyone. The celestial sphere is actually just flat Earth elevation angles. But the other thing that got me is Ptolemy also came up with the flattening of the sphere. He wrote the planispherium. He's like, you know how you get out a spherical coordinate system and put it on a flat plane? Boom, wrote a whole book about it. So he
The
was
celestial plane, flattening of a sphere.
planispherium.
Planispherium.
I haven't read this one, but I'm gonna look into it because it might be good.
Yeah, I'm gonna download that right now.
That's the it's pretty genius as a
Yep.
trick.
Well, plus also they said that when Einstein said that whether you use you think the stars are moving, the Earth are moving, you can still use this and you'll still get there. Shouldn't this be exclusive for the globe? I mean, if we're spinning, you shouldn't be able to use it if it's flat and it's stationary.
Well, as we saw with the celestial theodolite, all globe predictions start off with flat Earth baseline, and then
Flat baselines.
celestial corrections from there, right? Model corrections, best fit lines, spheres. So without the flat Earth starting point, there is no globe anyway. I think we see that all the way through.
But that's only on line 15, and it doesn't matter.
So what is a planisphere? Is it similar to like curvilinear, right? Where it's like a plane and a sphere? I don't understand what that means. A
It's,
planisphere?
I know it's an oxymoron, but it's one of the earliest like how to tell where you are on a star map, right? It gives you a star map, and based on your latitude, it tells you where you're going to see the star. It's pretty essentially mapping the sky before they could, and they give them out with like cardboard today and a pin push, and like, look, we give you a planisphere, right? But apparently, this is put forth based on this book, which also written by our boy Ptolemy. So he wrote the celestial plane or star chart in this whole big book published, and I don't even know how long ago. Doesn't even give a date. Yeah, I'll have to look into that, but that's where this whole concept comes in. Of course, from this concept, you have the astrolabe. From the astrolabe, you get the armillary sphere, et cetera, et cetera.
All right, thank you.
I think I'm with
Yeah,
Gally.
real quick, I have a question,
think-
Shane.
oh.
If you're using a model that uses lat long, are they all the same, or is there a different extra special one hidden within the lat long models, or what?
Well, that's the argument with Greenwich, right? So the whole point is, does it matter where you put zero at? That's what we got with Morty in the debate. He was like, "Oh, well, it matters. Didn't it can be arbitrary?" And it's like, is it arbitrary? It depends where you start counting from. That's what it technically means. But the point is whether it's universally like unified or whether you're using local coordinates. The historical record says that Ptolemy not only invented all these positions, right, but he had his own prime meridian. So he had his own personal like longitude lat spherical coordinate system that only he and his buddies used, and that was super successful. But then nobody used until 1712. It's such a weird historical record that like, okay, so you invented the whole thing, but only for you guys in your local prime meridian. I forget where he made it, but it was like his local city, and then everyone who was sailing around there would be able to use it. That doesn't make any sense to me. But that would work fine, and then you need to unify it at Greenwich to have that one as the zero, because all that happened in modernity was the Board of Longitude not only unified the need for longitude as a unified system, but made sure that zero started at the Greenwich meridian, which is where they had the Royal Observatory from 300 years before, when they insisted that they got it there from talking to some king. So
Yeah, I'm looking for that book right now, the Planispherium. If I find it, I'll let you know.
we'll just have
I'm
to
sure
let
I'll find that book.
Eric know.
Oh, he'll find it in a second. I'll see on the challenge.
There's so many more of these charts around. This is a whole presentation unto itself. I remember when I first looked into this and I speculated wildly. I was like, based on these and this, like, what if you just rode up to one of these, plopped your thing down, and then followed that bearing? And I look into it and I'm like, oh shit, that's exactly how they used them. Okay. All right, cool. That makes a lot of sense. So they don't tell you all that
Yeah.
when they're like, oh, we needed to unify it with longitude because everybody was crashing everywhere. It's like, oh yeah? Well, then how is everyone getting around with these wonderfully made custom maps and charts? And why did everyone have a compass rose? That's weird.
Yeah, I want to know what the heck those little points are. Like, just that depiction alone looks so strange.
Yeah, like what decided them to put it here? I was thinking it could be anywhere, but it's definitely not. Like this one over here and over here. They're obviously central points. Oh, this one's in the middle of everything. And then they're all like geometrically related to this one. Like this one links to this one, links to this one, links to this one. So if you can find your way to any one of these, you can theoretically find any of them, right? That's how it would work.
Are they the opposite angles from each other?
They line up with any stars?
Yeah, they are.
Yeah, that's
If you look at it,
the argument.
yeah,
I
like
think.
look how they connect with each other, right? They're opposite angles to each other. They're inverse of each other. So that one's south, right? Like if you go start in the middle, the very center, you go directly south, connects to that one, which is directly north.
Dude, they're all directly connected. Everyone directly connects to every other one. It's an elegant
Right.
system. So of course, yeah, I would like to see the underlying celestial infrastructure here because that's probably what it's based on.
Yeah, there's so much evidence for ancient maritime trade in the form of like foreign coins, like a lot of Greek and Roman, ancient Greek and Roman gold and silver coins, for instance, in India. So, they were doing trade. So I think that maritime trade has always been robust. So yeah, so they just made up, they, like you said, they just kind of publicized that tragedy so that they could force the system on the world.
That's what makes the most sense to me, especially after living through the past 5 years where they did that religiously all the time. They're like, you know what, we needed some fear porn. Do we recognize fear porn when we see it nowadays? I'll tell you. I'm like, this sounds like fear porn, guys. They took this one example and they put, pamphlets in the urinals or however they spread memes in 1700s.
How dare you recognize patterns?
Yeah, and the other thing too is that, if the Earth is locally flat, then shouldn't it be like a big bead with facets? Like you have beads with facets. So if it's locally flat, it shouldn't be round. It should just have all these facets. It's pretty lame.
I mean, that makes sense when I started looking at it like this, right? Like, oh, if I see a star, then it just depends on what time, and then you take this 24 hours divided by 360, and you get the rotational rate of sidereal time, and oh my god, that's how the whole thing works. I get it.
I like that last map. I really like that one.
I thought I had it
Yeah.
moving. I don't know what's wrong with this. It's supposed to be a video where the stars rotate to give the actual center.
That'd be a cool like thing to print out and toss on a wall. I have the dual hemisphere map that you were shown before with the little kind of like figure 8 in the center. Kind of, yeah, similar to that. It looks like that, but it has like a figure 8 from one side to the other. The P-Tals map.
Yeah, they're definitely like those are star maps to me. Like if you want to map the hemisphere, that's how you'd have to do it, and it's a perfect match for like the perfect match for the land.
Yeah,
maps.
top right map. I have that on my wall right now.
You know,
Top right.
one thing I don't understand is that when you see these star trail circles, you know, they're perfect circles. I don't know how you could have that, because I think you can only have that if the Earth was stationary and spinning on its axis alone. But according to the globe model, and not only is it spinning on its axis, but at the same time, it's actually orbiting the sun. So I don't see how the stars could make those perfect circles. And then also the zodiac constellations, you know, have been the same for 3,000 or more years because ancient people have drawn them and recorded them and described them. So, you know, I know the whole theory of everything so distant that it remains the same for centuries and millennia, et cetera, et cetera. But really, honestly, it doesn't make any sense, like to the common sense.
I think the way it's wobbling, Lily. The wobble, you know, it has 4 different degrees of wobblarity.
I was gonna say we're talking about the axes of wobblarity and contention here. How it's doing all 4 of those motions but maintaining perfect concentric circles is a mathematical conundrum, I guess.
Yeah, have they ever made a model that actually can do all those motions?
If you look at Wikipedia, there's a really funny animation that I like to show people of it supposedly working.
It's interesting that astrology only applies to those constellations, right? Those 12.
Yeah.
So I got a question.
It doesn't make sense to me if it's just in the equator. It's like, I wonder if there's special. Never mind. Sorry, speculating. Go ahead, Brian. Speculating. Go ahead.
So over here at the concave Earth here, they all use the same stars that we do, and they actually, these circle maps here, they actually say these are concave.
I know. I know.
Yeah. So here's the thing: all the models that use the lat long, right? Lat would be, you know, the elevation angle to a star, and then the longi would be the time in which the star, or like the position of the star at the time, right, to find the geographic location. All these models use the same exact coordinate system. There's no difference between any of them. The only way that you could tell the difference is by, you know, merging the celestial and terrestrial through, you know, timing of intersections of stars or something like that.
Hey,
But
Dave, I think you're hot, Mike.
yeah, it's just it's insane that they don't realize that they're just using the same thing and just blindly asserting causal mechanism.
You mean it's not mutually exclusive between those projections, those coordinate projections?
No, I mean the whole purpose of it is to project it onto different things. It all represents. So here's the thing: it's all
It would
derived
be
off
useful,
of single
right?
observer zenith measurement. Well, it's all derived off of single zenith observer of measurements stitched together by the fictitious observer at the celestial sphere. If you're using a model that's tied together by a fictitious observer to make everything work, then you can explain whatever, you can have it whatever shape you want. It
It's
doesn't matter.
equivalent, right?
And there are some crazy shapes to look at that you can pull up online. There's even a heart shape.
Dude, so here's
Yeah,
here's my map projector that I just opened a star map in, and we can play with all of the other sort of projections. This is what I was doing. The one that I think is, they call it the Got Magnalio Azimuthal 2 hemisphere. That's this one. We had that one a bunch. And then there's the concave one, I think is called let's see here if I can find it. Nicolasi Globular 2 hemisphere. Yeah, it's this one. So like it's got the 2 converging poles essentially, like so it's got the whole thing is based on a spherical coordinate system still, but it plays the northern and southern hemisphere, and it has the projection emanating to the point where it converges the longes in a different way. This is different than the orthographic globe, right, which we can do a different projection on. I think I could do 45. Yeah, move that around. That's a weird one. Regular Winkle Snidel, cylindrical. Mercator, Vitoski, that's a good one. That's a good one. Wagner 4. Let's see, we got tabular hyperelliptical. That's a good one. Tabular G1. Tabular cylindrical. I don't know why tabular needs 17 more. Got the Strebe equal area. That's a good one. That looks like an apple a little bit. Apple Earth. Times Atlas. Ermov cylindrical. Toddler. It's just another spherical. It's a transverse Mercator spherical. That one looks a little weird. The stereographic two hemisphere is what I use most of the time to represent the globe. The actual globe map, as people get confused, is called the orthographic. That's this one, but we need it at a different angle, I think. 45 degrees. There we go. Oh, it's already at 45. Center that.
Looking at all these shapes, you're like, people have been really doing these projections onto all these different shapes for funsies. That's a trip.
Well, all right. So I don't know why, and most of these are necessary. Like Soloviv modified Bonnie. Let's see what this one is. Who the hell needs this? In what world was this necessary for something? To have a unified, like nobody uses this, and yet here it is. We got Heart Earth, right? This is the state.
I have a map like that, actually.
Yeah.
That right there is what concavers believe in. Like that's what they think the torch field or whatever it is, and right there in that butt crack is where the sun. That's where the
you know what's funny is
but even that's just a projection.
Yeah, it's
That's
also
dual pole.
actually, dude, the azimuthal equidistant, like the AE. This is the AE right here. And if we get a little creative with it, when we start moving our center projection point, we get what's called the actual concave Earth, right? If I go say here, boom, this is what they have it, right? And then 23. So this is the concave Earth map, but it's still a freaking azimuthal equidistant. It's just centered at 23 lat instead of 90, right? Like, because it's centered at the North Pole at 90 north. If you center it at 23 north instead, you get concave Earth. So all just.
So the idea is that you can nearly make the projection onto any shape that you want. The only thing that's going to happen is it's going to skew, like for example, the shapes of the continents or what have you based on what.
So when you're putting in a latitude, or is it changing the fictitious observer at that latitude, or is it still the center?
No, well, the azimuthal equidistant always has to have that center because that's part of the projection. But like the point of the projections and translation from a sphere is that the coordinate system itself is spherical, not that the globe is spherical or that Earth's a globe, and that's why the globe is the only unadulterated shape. No, the globe itself is an orthographic projection. Orthographic just means like one for one, right? So it is the actual model of the celestial sphere created from the terrestrial sphere, right? So latitude, longitude is curved and is spherical, and that's what's causing the distortions. Not that Earth be sphere, or that it's because Earth is a sphere. It's because latitude and longitude is a sphere. That's why we can translate to and from, back and forth all day with no error.
Right.
Yeah, and for the record, that goes for the AE map as well.
Absolutely,
Boys.
absolutely.
Yeah. For the record, because there's some people that don't seem to be getting that through the old soul.
Yeah, no one lives on a flattened out spherical graticule. I hate to tell everyone, this is not the Earth.
Right.
Okay? Yeah. It's not even the correct position of all the stars when you do it this way because they're warped outside.
As an orb enthusiast, what would it look like if you took the projection and put it on like a perfect orb? Has anyone ever done that?
Perfect orb. I think I can do. Hold on, let me see. I have. You know what? Globe Tissot's. Wait, hold on.
I don't know if this program does actual like 3D projections, but
Oh, do you see this?
I was making a globe joke.
Do you see that?
These... rectangular.
Well, no. So these. All right. There you go. So I imported a Tissot's indicatrix scale model so we can see distortion. So when we're on our graticule here, we can see that the distortion towards out here, of course, gets more distorted, right? So on the orthographic globe, or even in the original coordinate system, it would be spherical and all the same size. I lost my overlay here. Projection. There we go. Orthographic globe. So if you do something like this, then you can see, oh, look, they're actually not distorted because Earth be globe. And it's no, they're not distorted in the spherical shape because that's the core coordinate system. That's the shape with which you're projecting. So even if this one gets distorted, smaller. Yeah, this is just G projecting.
Remember one of the earlier presentations I saw when joining Ether Cosmology was like the war of the maps, how maps were used to propagandize, make like certain countries look bigger and more menacing.
Yep. But that's when people didn't understand this particular like phenomenon, right? Because even on the Mercator, you get distortions. You got, in the middle, it's meant to be equal over here, but look over here. And then of course the poles are all fucked up. So when you're trying to tell everyone they live on a map, of course not. Nobody lives on a map. Nobody lives on a sphere either, right? It's just because we have it represented as a 3D terrestrial sphere based on the celestial sphere doesn't mean that's actually what the world looks like. And you can tell from the Tissot's indicatrix circles here how the distortion is applying in each type of projection. Cool. Good stuff. Stop sharing there. Close my map. Everyone should
Awesome,
download
Prezi,
G
bro.
Projector. Thank you, sir.
Thank you, Shane. Awesome.
Thank you, Shane. That was great.
Thanks, everyone.
And it's time for a coffee break.
Oh, Lily G, are you gonna run a coffee ad?
Well, I don't want to get sued, so I'm doing it, even though I don't really want to, but I will. I don't want to get sued. So here we go, folks. Coffee ad. Done with handcuffs on in a dungeon, from a dungeon, coming to you from a dungeon deep somewhere on flat Earth. Oh yeah, anyway, just to be serious for a second, I stubbed my toe last night and I was like, oh my God, that hurts. And so I was like, oh, it's too late to drink coffee because, you know, the brush-tailed coffee, it's a cure-all. It cures everything, even a stubbed toe. So I thought, I can't drink coffee. What if I just open the jar and just smell the coffee? So I did. I smelled the coffee, and you are not going to believe it. Boom. In 1 second flat, the stubbed toe stopped hurting, and I was back to normal. So, folks, get your supply of brush-tailed coffee. It's super duper delicious. And for those of us that need coffee to make our brains work, you can do it with something a coffee that's fair trade and organic and shade grown, etc., etc. So get yourself some brush tail coffee.
You're carrying stub toes all over the flat earth, I guess.
Hey guys, I have a question.
What up, T3?
What's going on? So, Shane, with the projections, when it's done on a flat surface, like you said on like the AE, when you said that they're spinning, right? The stars there when they're spinning, are we saying that they're spinning like just as a disk, you know, all at once like that? And the reason I'm asking is because the next question is that actually correct? Like, does that align with how we see them?
No.
No, right?
No.
So check. Okay, so here's my question. The next question: do you think it's possible to do like to work with somebody to do like an animation to see how it could work if they were following some type of magnetic you know, toroidal geometry type of thing to the effect that we would see it that way? So we have both poles spinning and then the center, you know, so looking different because it looks like the bar magnet, right? The bar magnet geometry.
I think we kind of get what we get now because of the magnetic toroidal field. It's just a tougher way to explain. I did a presentation a while back on like the actual orthographic so-called true position of all the stars in the south. And then I was kind of linking them to the north, right? And saying that the southern sky looks like a darker, dimmer, stretched out projection of the northern stars. So you have constellations that sort of mirror themselves in a distilled, dimmer offshoot that looks like it's distorted and stretched. And that's how you sort of get it. And I think that happens at the equator because of the, like, say, toroidal flip zone, which you'd have in like toroidal geometry in the middle. When you have the poloidal field going around and the toroidal influx zone, you'd have the same thing. And then that would cause some sort of flip to get in the south. But I think that the end result is that we see it as if it's two hemispheres with the south mirroring the north. I think that's how we would see it.
Right. So is there a way does anybody know anybody who would be able to like model that to where it could match? Because I think if we can do that, if somebody can do that, I mean, it would kind of kill that argument that, you know, things don't match up, you know, because the argument is that how we see this, it's completely impossible if it's not a sphere, right? If the planet's not a sphere. And I think that does make sense. I'm sorry, go ahead.
Just you, brother.
Oh, I thought somebody said something. Yeah, I think that argument makes sense. But if we can
I don't think that is the only way that being a globe is the only way that it would make sense. I think that we have to exercise our imagination. There could be all different kinds of ways that we just don't know what phenomena is happening. I mean, when you think that, you know, in the sky, there's miles and miles of microscopic quartz dust and silica dust, which is not fiction, it's there. So think about how it would distort anything visually. And like when Shane said that if it's a toroidal field, then yeah, you're going to get that reverse mirror image.
Yeah, well, that's what I'm saying.
Like the quartz dust and the silica dust, miles, hundreds, thousands of miles of it is going to have some effect, visual effect on all these celestial objects that are luminaries.
Right. And then there's the matter of how we see it is not how it is. I mean, just like, you know, the railroad tracks, how we see them joining together, that's not how it is. And so there's the perspective. So it's almost like we're trying to map out a model of our perspective, and what you end up with is a map of a model of your perspective.
Yeah, exactly.
Yeah, right. But that's how we see it. So that's actually kind of necessary. You know what I'm saying? So I'm not saying that the way that Globers are saying it is the only way it is. What I'm saying is the way we see it, can we model that on top of a flat surface? Because if we can do that, then we shut them up about that.
Well, I mean, if I argue we observe in a hemisphere, like I would lean into spherical coordinates more than anything, because it's a good way to mathematically describe the hemisphere that we see and deal with, I think. But like, so the celestial theodolite presents a different idea for that, because you have to differentiate between visual space and the visual field then, because we found out, 69 miles per degree would only be an optical effect since the time and occlusion for the mountain happens based on the physical baseline. So that kind of threw us for a loop as well. Like, all right, well, it wouldn't matter then where you appear to see it. It only matters where it is. So then literally what we could have is coplanar, right? A star field that's coplanar with flat Earth. Like that could be the actual reality.
That's what I'm saying. And so, okay, so now you're with me, because that's what I'm envisioning it as. I'm envisioning it as like the surface, and then above that you have a planar star field. But the thing is how we're seeing that.
Yeah, we never observe it that way.
From pole to pole.
Exactly.
From pole to pole, we see it as the geometry of a toroid, because at this pole we see it spinning this way, at the other pole we see it spinning opposite, so to speak, and then in the middle we see them going, up and over and not really spinning at a point, right? That's the same thing as a bar magnet geometry. So is there any way that we can use bar magnet geometry to actually map that shit out in a planar star field over the surface? Because if we can, then they can't say that we can't, that it's impossible unless it's a sphere. That goes out the window completely.
So it's tough because it's a coplanar field which nobody ever sees coplanarly, right? We only ever see it spherically because of the limit of our vision and optics. So we're definitely stuck, and we haven't really accepted that as the truth until the celestial theodolite, right? Like, well, we're like, well, damn, it must be. If every measurement comes up with the occlusion timing that matches this baseline, then in reality it must be at this position, right? We must be looking at coplanar star fields. But always the most interesting questions, dude. And yeah, do you want to just solve everything? Sure, let's take a shot. What do you think?
My bad. That was it. Pass the mic.
That was a great question, Joe. It's the stuff we're thinking about now, right? Like mulling it over and trying to figure out how to put them all together.
Nice.
Nice. Then we'll wrap it up for the night. Then I'll close out the stream unless anyone's got anything else.
Nah, man, great Prezi.
Fellas, thank you.
Thank you, Shane G.
Welcome to the show where you don't know if it's part of the show. Welcome to the show. If you don't know, it's part of the show. Didn't they teach you to reach for the stars while opening up the bars and keeping you chained down with mortgage bills and cars? Vaccines for your arms, kids sounding like supercharged, caffeinated hate-filled scars and rage-quit repertoires. No answers for yards, caught up in emotion that's not even yours. Imposter truths like impeccable retards, lined up for your serving of Gish Gallop and wars. No remedy can save the lost, in love with the yarn. I'm tired of walking into refracted shards, poor science displayed by disgusting bards. Soaked in sin with your dupe is delight in a new hand of cards. Been so long, seems like for love I'm just too hard, that's it. Welcome to the show where you don't know if it's part of the show. Welcome to the show. If you don't know, you don't know. Intoxicated 8 makes you believe you're spinning in space while you have no shame or grace. It's a disdainful state I used to contemplate how to save myself from my own self-hate. Wonder why I was even made with a dreadful fate, forced to try and awake with a full plate. No one to help me stay awake or educate. I've had to liberate and fight through hidden gates. But my brother, heaven could never be late, and rockets don't work in space. It's all fake, the show is on Mars. It's a joke, but you're too far gone, it won't be long. Fepe's beak is strong. We have our song and we march along like streams of knowledge leading to God's holy pond, and lives of truth that hits the bong and sings the song, turns mankind from the wrong. We come in peace with a holy gown and all of us wearing our holy crowns. Said the earth is flat and we probably just won't get along. Just to go along, I said, welcome to the show where you don't know if it's part of the show. Welcome to the show.